Hi, everybody. We're into chapter 2, and that means we're actually going to start doing some calculus today. We're starting off here in section 2.1, and we're going to be talking about rates of change, tangents, and actually a little bit of integration as well. What we're going to be doing is giving you a little bit of a teaser of why we're going to start off a study of calculus by focusing in on limits. Limits are going to be these things where we approach a certain value little by little, and today is kind of motivating. Why are we doing that? So we're going to start off here. The first topic that is on the section is called the velocity problem, and the second one is the tangent problem. But the velocity problem is framed as a problem because normally when we talk about velocity in everyday life, it's a little bit ambiguous whether we're talking about average velocity or instantaneous velocity. Average velocity would be you take a 65-mile trip and you complete that trip in 1 hour. So your average velocity was 65 miles per hour. Realistically, though, you know that at driving, there were some points in that trip where you were over 65 miles per hour or under 65 miles per hour. And so the average is just what happened over the entire trip. And it's just a fraction, it's a ratio. A lot of times we phrase this as distance equals rate times time. In terms of like the velocity problem. But yeah, you could also interpret R, the rate at which you're going, as the distance that you've traveled divided by the amount of time that you traveled. And that's more about average velocity. Whereas cars have these cool things called speedometers. And the speedometer is giving you an instantaneous velocity. At any given moment, ideally, your speedometer would be giving how fast you are truly traveling. And really what we're going to be doing here is, through a limiting process, taking the way that we would normally calculate average velocity and shrinking it down enough so that it approaches instantaneous velocity. And it's the instantaneous velocity is kind of the new calculus stuff that we're learning today. Let's go ahead and start in on this problem. Example number 1. A piece of rock falls onto a 256-foot deep canyon from its rim. So we got the rock starting up here, it's going to fall down. The distance below the rim at time t is 16t squared. And actually, as we will discuss later on when we learn how to take derivatives and antiderivatives, this is actually a pretty realistic function to describe how a rock falls, because the way that a rock falls is determined by gravity, and gravity is when you're on the surface of Earth, it's a pretty good constant, 9.8 meters per second, or roughly 32 feet per second. And this distance formula actually comes from that 32 feet per second in a downward direction kind of a thing. We'll talk more about that later in the class. Okay, d, the distance, is measured in feet, and t, the time, is measured in seconds. we are going to estimate the instantaneous velocity of the rock after 2 seconds and the velocity of when this thing actually impacts the ground. So what are our options here? We've got this function d equals 16t squared, which means if I'm just gonna, draw a sketch of what I think this would probably look like, it's gonna be a parabola. It's gonna hit the origin because we don't have any pluses or minuses there. It's gonna be stretched out. But yeah, it's a parabola. And if we are going to estimate the velocity here, when we're looking at a graph with t and that's not a t, that was a y. T and d of t on this axis, or a y value here, whatever you want to call it. Yeah, the slope of the curve at any given point is the instantaneous velocity. But when we try to calculate that using the way that we normally calculate slope, bad things happen. So, for instance, what we could do is use this formula and say that we're trying to get something that's close to after 2 seconds, it's in the air. So let's go ahead and calculate d of 2 real quick. D of 2 is 16 times 2 squared. And that's going to be 64. Whoops. 64 feet. And if we were going to try to calculate the slope based off of one point, we would get this really silly thing where, slope is normally rise over run. Whoops. Which would be a difference in y values over a distance in t values. And so we'd have this silly thing like 64 minus 64 over 2 minus 2 for the, the t values that you'd put in. And you get this fraction that just looks like 0 over 0. That is an indeterminate form and doesn't tell us anything. So kind of one of a better estimate than that would be, let's calculate d of 3 real quick, just some point that's 1 away. And that would be 16 times 9, which, good grief, do I even know what 16 times 9 is? Is that 144? I think it's 144. Feel free to laugh at this point if I have that wrong. I'm not in the room. You're not going to hurt my feelings. But I believe this is 144 feet. That's a horrible thing to say. But using these 2 points now, we could calculate, again, the slope, rise over run, by taking the difference of the two y values, 100, well, yeah, let's do this way. 144 minus 64, and then 3 minus 2. And on the top, we would have 80. And on the bottom, we'd have 1. And this is 80 feet per 1 second. And so this is actually an approximate instantaneous velocity. I am going to now take the opportunity to go to Geogebra and show you this cool thing that I made. All right. Let's go ahead and get rid of this line, this line, this line. All right. Yeah, we can leave D there. All right. So these numbers actually worked out the way that we were hoping. But yeah, we've got this parabola in green. This was the first point. This is actually where we're hoping to find the slope. And this was the one that we utilized. I think if we make a line through A and B. We can get this blue line. And if I zoom in a little bit, you'll probably be able to barely see it, but this is actually what's called a secant line because it crosses the original parabola in two spots, one at A and one at B. Now, this is not a tangent line because a tangent line would only touch the curve at the point A, at least locally, so that it gives a perfect estimate of the slope there. But notice that this secant line, since it goes from A all the way through B, does not give a perfect estimate of the slope there. Another thing that I did for fun was, instead of going up, maybe we would go backwards and calculate the slope between 1 second and 2 seconds. I think that's this line. Yeah. And you can see that the one that goes from D to A here has a shallower slope than the one that goes from A to B, because generally as a quadratic progresses, it continues to get steeper and steeper over time. Both of these would be decent estimates. I think, the orange line here has a slope of 48. The blue line has a slope of 80. But what we're hoping is to have a better estimate than either one of these two. And the way to get a better estimate is to have a line here that I'm going to get rid of that line, where we can vary that extra point. Other than the one that we're trying to estimate, we've got this point C. And let me go ahead and turn on the values there so that you can see here. We're going to get better and better estimates for the actual slope here at A by getting C closer and closer to A. And this is actually the limiting process that I was talking about. Limiting means that you're just approaching a certain value over time in terms of the x direction. So we would say that x is approaching 2. In this case, we are approaching 2 from the right. We could also start over here and approach 2 from the left. But what we should notice is, as I'm approaching, we can look at the difference quotient part at the bottom here, where we've got 2 y values on top and 2 x values on the bottom. As I get closer and closer here, you can see that we're approaching 59, 60, 61, 62, all the way till we get here, and it looks to be about 64 when we're there. And then it continues to grow over time up to, 80, what we found before. But the limiting process, whether you're coming from the left or from the right, seems to approach this value of 64. Now notice sometimes, boom, there's something wrong with the way that I coded this, because I'm getting a 64 here, but realize that 64 minus 64 is in fact 0, and 2 minus 2 is in fact 0. So this is what I'm talking about with like the indeterminate form. This is a problem, and it's the reason why we can't calculate instantaneous velocity the same exact way that we do average velocity. We get this indeterminate form, which is bad news. That's fine. Was there anything else that I wanted to show you on this one? Not right now. That's the idea of limiting. So what I'm going to show you next is, boom, scrolling down a little bit. Look at these intervals. So now we have intervals. These ones are all on the right-hand side of things. They're intervals from 2 to 2.09, and that 2.09 get smaller and smaller and smaller until we're just getting intervals that are closer and closer and closer. That is the same thing as from the right, approaching these values so that your x value, here's 2.09, 2.08, 2.07, all the way in, and we're approaching so that we get closer and closer and we get a better estimate. Here's what that looks like numerically, just calculating those average velocities. So that you guys know, there's the Greek letter delta here hanging out in front of D and T. All that delta means is that you're taking the difference between two D values or two T values, which is, the rise over the run thing. So delta is just a short way of saying difference. And here's the table of things coming from the left. And notice as we shrink that interval and get closer and closer to the value that we're hoping to approach, we get a better and better estimate of what that instantaneous velocity actually is. Okay. And for part B here, I think I've spent too much time on this problem. At the velocity of impact, all you would need to do is think about, okay, one has the distance traveled been 256. We subtract that from both sides, divide by 16, factor, and that would be at t equals 4. And you could do the exact same thing for estimating the instantaneous velocity at t equals 4, meaning that you get closer and closer into values that approach 4, either from the left or from the right, would be a good way to estimate that instantaneous velocity. Okay, so now here I want to talk about this thing. It's called the difference quotient. It's a slope fraction. And there are two ways that we might explore this in our book. And I think, both of them appear at some point. I'm going to start using this limit notation. Actually, let me make this colorful. The first one can be pink. The limit as x, those are x values, approaches a will be some x value in particular of f of x minus f of a all over x minus a. So this is the difference quotient that might seem pretty familiar. What we're doing is, this is this limiting process. X, the way that we say this is x approaches a over time. And yeah, maybe I do want to draw this real quick. We could have some kind of curve here. And the idea is we've got some x value a, and that's where our important point is. That's the one we're trying to estimate. And then, yeah, we're basically trying to find a slope. And then x is this other value, x value, but it is approaching a, we're scooting over towards it. And as that happens, we get better and better estimates of the actual slope. And, if we were to go up here, we would have a point f of x, as a y value, f of a as a y value. So that's where those things are coming into play. The alternate version of this looks similar, but we will have the limit as h goes to 0 of f of x plus h minus f of x over h. And in this context, we want to interpret h as the distance between kind of a and x in the previous problem. But yeah, in this context, x is actually behaving as our point of interest. I'm going to go ahead and draw a curve there. So x is behaving as our point of interest, and x plus h is another point over here. We're still approaching x because the limit here is as h goes to 0. So we're shrinking that distance. But this just is another way to formulate that difference quotient, where now we only have one number on bottom that's going to 0, and it's the distance between the two x values that we were working with. This one will be utilized more often when we're actually using limits to calculate derivatives. Okay, so if there are any questions at this point, go ahead. I would say, freeze this, and maybe Ali can help you figure any of this out. Cool. All right, so now we're moving on to topic number 2, the tangent problem. And this is, without context. We're just in math context. Tangent just means you're touching the curve at one point. So you can be tangent to a semicircle, you can be tangent to a parabola. In both cases, the red lines are tangent lines, the green lines are secant lines. And we could do example number 3 here, but I'm kind of just thinking we just look over this one instead of doing it, because it's pretty much the same thing that happened in example 1. Our instructions are construct difference quotients to approximate the slope of the line tangent to the graph, blah, 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 at the point 1, 2. So we're looking at our point of interest is 1, 2, our x value is 1. So on both of these, we would be trying to approach 1 as an x value. And in this case, we're seeing this formulation of the difference quotient, where we have f of x plus some distance minus f of x just itself. Here, our point of interest is 1, and the distance between our point of interest and some other, arbitrary point, they just decided, let's make that h distance 1 for this trial, but they're gonna change it to 0.5 pretty soon, and then it shrinks and shrinks even more very, very soon. This is what constructing those difference quotients would look like. And notice that, yeah, when you get closer and closer, you end up dividing by a smaller and smaller number, which in effect makes it look like you're multiplying by a bigger number. But yeah, we get kind of an awful estimate when we go all the way out to 1 unit, and then we get progressively better estimates as we get closer and closer, and we shrink that h distance between the two secant points together. Visually, here is f of x in red. And again, I've got w functioning as a slider. B is just the point w, f of w. And yeah, when we go 1 unit away, all the way out to 2, the slope of this line is -4. And actually at this point, we have a positive slope. So we get better and better estimates as we get this point closer and closer to A. We have that, nasty sticking point when this thing actually is equal to 1. The line function just is like, I don't know what to do. But yeah, same exact thing as last time, so I didn't want to dwell on it too much. But I wanted to include this because it has the alternate formulation of the difference quotient. And really the only difference is that instead of two numbers on bottom, we just have one, and it's just the distance between the two things. Anyways, let's keep going. On to example 4. Show that the slope of a tangent line of the absolute value function at 0, 0 can't be inferred from a table of difference quotients. So the main rub here is that from the left-hand side, we consistently have a slope of -1. But from the right-hand side, we consistently have a slope of +1. And as you approach from either side, we're always going to be -1 from this side, and we're always going to have +1 from this side. And we end at this sharp point. This sharp point is actually in calculus lingo called non-differentiable. You don't necessarily have to know that right now, but what that means is that the left-hand limit does not match the right-hand limit, and therefore the overall limit from the left and the right doesn't exist. In the previous problems we looked at, those things have matched, and it was great. And we get the nice continuous feature of these things. They're curvy rather than pointy. When we get these sharp points, that's a problem for finding a slope that makes sense. There's not really one tangent line that is the exact right answer. It's just not possible. So, there's some extra stuff there. Feel free to pause and look at that if you want. But absolute value line or absolute value function is not differentiable at that point. So while this idea of limiting is a very powerful idea, there are definitely functions out there that don't always behave well. And yeah, we'll see plenty of those in this class. But the main idea in the velocity and tangent line problems, and actually the one that we're going to look at real quick here with taking an integral, is that the true value of a quantity that we seek, so this instantaneous velocity or the slope of a tangent line, can be approximated to any desired degree of accuracy through the use of smaller and smaller increments. And so that's the big idea there. That's kind of the big idea of the section. Now, let me go ahead and example 5. I did not put a GeoGebra link here, so bear with me for a second. I'm going to go back to GeoGebra, go to my profile. Actually, yeah, let's go to my favorites. Yeah, calculus book is one of my favorites. Great. And then tangent line fail. Okay, 2.1 example 5. Great. Let's go ahead and open this in the app so we get a little clearer picture. Gosh, and the text on this is tiny. Whoops. Okay. Let's blow that up to 20. Sounds good. Okay. Here we're looking at something kind of the flip side of calculus, where as before we were talking about instantaneous velocity, which is very related to the derivative. Here we're going to be actually accumulating area under a curve. So I'm going to get rid of these. We're accumulating area under a curve over time, and this is going to be called an integral. So the specifics of it is we have this function f of x equals x to the 3/2 power on the interval from 0 to 1. And what we're going to do is divide this interval from 0 to 1 into smaller and smaller subintervals and estimate the area of this region R, because right now, normal geometry doesn't work. We've got two straight edges here and then one curvy edge that doesn't really allow us to use like a formula for the area of a triangle. But what we can do is estimate the value of this using rectangles. And the idea again is that as we increase the number of rectangles from something small, which, you know, using one rectangle here is a pretty awful estimate of how much area is actually underneath that graph. But if we continue subdividing that interval into smaller and smaller delta x values, so difference in the x's, we get a better and better estimate. Here's what it looks like with 50 rectangles. You know, you can see that we're missing some there, but this is a much better estimate of the total area than what we started off with, say with 4 rectangles. And that's called a lower Riemann sum. This one's an upper Riemann sum, where again, we could do the same thing with rectangles that over approximate the function, but you know, we get better and better as that gets closer. So the actual area, the integral, which is still a mystery right now, is 0.04, but as you increase, you can see that this lower sum gets closer and closer to 0.4, and so does the upper sum. Both of those approach 0.4 over time. So again, later on in this course, I think it's like chapter 5 or chapter 6, that we start talking about integrals, you know, very similar to the difference quotients that we looked at, where we write these limits in front of them. There's going to be a limit definition of the integral, which is gross. And in order to gross you out, I'm going to write it now. The limit definition of the integral will look like the limit as n goes to infinity of the sum of a bunch of rectangles. The number of rectangles that we have is going to start at 1 and it will go all the way up to n, however many rectangles that we have. But notice that the limit is going to make n go towards infinity. So we're going to approach an infinite number of rectangles. And the entire time we would be multiplying a y value for a certain rectangle, evaluated at something called a sample point. And we would be multiplying that times delta x, the difference in x values for each one of those little rectangles. And actually, I mean, if I want to be super, that would be evaluated based on whatever sample point we are as well in general. Normally, we just leave delta x as the same thing for the entire interval. But yeah, limit definition of the integral, looking pretty good. Don't worry, we'll get into that later. But yeah, these limits are kind of the central thing here. Cool. Every limit scenario, when described verbally, contains phrases of a dynamic nature. H approaches 0, or x goes to 3, n grows without bound. That would be this one, n grows without bound. Yeah. In a less mathematical setting, phrases might be something like mortgage rates are expected to approach 5%, or, you know, assuming the national debt keeps getting bigger, but whatever. Yeah, this is limit notation, where we have the limit as x goes to c of f of x equals L. X is just our normal variable. We are approaching an x value of c. So this c is some specific x value. And the L here is the specific y value that we would be approaching. but this is just the notation. And actually, since this is not notated from the right or from the left, the intuition that you'd want to be thinking about is that we would be approaching this C value, which is an X value, from both directions along the curve. And as we approach C in the X direction, hopefully we would be approaching the value L in the Y direction. You know, to be honest, I did not get to practice this stuff or look at it on Friday. So what I'm going to do, which might sound really weird, is I'm going to show you the limit definition. Well, actually, the epsilon delta definition of limit. And I don't, how much time are we at? Oh gosh, it's 5 o'clock. It's 5:05 already. Do I have the limit definition of, let's see. If I can find it on GeoGebra, we're gonna do it. Here we go. All right. Boom. Let's just do this, and this will be a good way to wrap up, and we can, ask questions, of Ali, and then when I get back. But okay, I'm having second thoughts because we're introducing new letters like delta and epsilon, and I haven't even shown you that formulation. But the idea here is that we have delta. Delta is going to be some positive number that gives us a bound on X values, and epsilon is going to be some bound on Y values. And yeah, I am making a complete U-turn. In order to do this well, I need to have the formula at least. I guess I could look in our book. But what's going to happen when a function actually has a limit, guaranteeing that delta is a certain value will guarantee that we're in a certain Y range. Yeah. All right. Probably we will talk about this tomorrow when I am in class, live in there, and we'll talk more stuff about limits. But I think we got to a good spot. We motivated why we use limits in calculus, because in general, the true value of the quantity we seek can be approximated to any desired degree of accuracy through the use of smaller and smaller increments. That's the idea of limits. And yeah, we'll see you tomorrow, and we'll talk more about what limits actually are and properties of limits and all that good stuff. All right, so have a good class. At this time, if you guys want to review anything or maybe look at your homework for section 2.1, that would be a good use of class time. All right, we'll see you later.